All right. Oh, okay. Couple scragglers.
Is it on?
Yeah. All right. Okay. No. Yeah.
Good morning. Good morning. Good morning. Our topic today is stem cell science and its application. And I have the pleasure of introducing our speaker, Vivian Polkinghorn. And she may look familiar to some of you because she's been a member of Midvale since elementary school. Who knew that one of our youth would grow up to be an expert on stem cell science? She told me that her interest in biochemistry began in middle school when she went to a summer camp that was sponsored by the University of Wisconsin in Madison. And she graduated in 2020 with a BA in biochemistry from Lawrence University. She now works for a company that focuses on differentiating stem cells. So we're going to learn all about stem cells and related cell types, and she's going to cover the past and current use of stem cells and where this developing technology might be going in the future. So thank you, Vivian, for making time for doing this, and let's give her a warm Midvale welcome.
All right. Hello, everyone. Yes, so I'm Vivian. And this is my first time doing a presentation since college, so I apologize. But yeah, some quick ground rules. So I'm not gonna, if you could hold your questions to the end, that would be great. Unless if your question has to do with like comprehension. If I casually bring up some random jargon and you're like, what the heck is that? I might be completely blind to it because I do say it all the time. So please, in that case, raise your hand and I will just say whatever you're asking about into the microphone so people at home can hear it too. Um, but yeah, with that in mind, let's get going. Oh, all good. Yeah, so I'm just going to quick go over kind of the composition of this. So we have a couple definitions that I need to cover really quick before we start. They're just things that I'm probably going to say a couple times that I would not expect anyone to know prior to this. Then we'll jump directly into what stem cells are. We're going to go over a little bit of the history of some of the kind of more important events that have happened that have to do with stem cells. We'll talk about some ethics because that always has to come up when you're talking about stem cells. And I'm going to briefly talk about regulations, but it's not really my cup of tea, unfortunately. And then we'll get into the fun uses bit. So, oh, sorry. I've never had one of these before. It's very odd. Okay. So this is a whole bunch of words, but just really quick. So I'm going to talk about cell lines. And the easiest way to think about them is basically a cell line is a group of cells that all came from one place. So most of the time it's a single cell that has created a cell line, and now all of these cells are basically like little clones of that cell. Every now and then you'll get a cell line that's from a couple of different cells that originally started it, but usually it's the same donor or the same starting material, basically. And then potency, you've probably heard the word potency before. I'm going to be using it a bit different. So for our uses, potency are the number of fates a cell can have, or basically, if we start with a stem cell and it can create 3 different types of new cells, it would have a potency of 3. Right? I'm not going to be using numbers a whole lot. I'm mostly going to be using totipotent and pluripotent. So totipotent means that a cell can turn into any cell type within your body. For humans, it's just zygotes. So when your sperm and egg meet, they create a zygote, and that cell creates all the rest of you, right? So that's what I'm going to be talking about if I say totipotent. And then pluripotent is a cell that can make multiple different types of new cells, but it can't make every cell in your body. And that's what most stem cells that we use are, right? They can make most things, but they can't make everything. And then I'm going to, obviously, in my intro, we use the word differentiation. What the heck is that? So that's just you're taking a cell and you're turning it into a different type of cell, or you're creating a different cell from it, basically. Yeah. So this is just like a quick example for cell potency because it's kind of a hard idea to get your head wrapped around, and I will be using the term pluripotent specifically a lot. So this is our zygote, our oocyte and sperm, and this can turn into anything. And then a blastocyst is 4 to 7 days after your oocyte and sperm meet, you get a little blastocyst. And these guys are pluripotent. They can turn into most things in your body. And from here, there's 3 basic branches that cells kind of split off from in your body. So there's your ectoderm, your mesoderm, and your endoderm. And we don't have to worry too much about what each of these does, but basically these are going to have separate types of cells in them that also can divide and turn into more cells. These are also sometimes stem cells, sometimes they're not. We'll get into that in a little bit. But basically, there's kind of a middle step, and there could be multiple middle steps before you get to your end product of, say, a pancreas cell or a red blood cell that cannot create other cell types. They're just whatever they are. So, yes, and now we can get into exactly what stem cells are. So they're cells that turn into other cell types. They're pluripotent, but they can also reproduce themselves, which is important. Most of the cells in your body that are just straight up like a liver cell, it can't make more of itself. So basically, our stem cells are where a lot of our healing properties in our bodies come from. You have a stem cell, it can create even more, but it can also create whatever specified cells your body needs for healing mostly, but also when you first grow. This is where all of your cells come from. And yeah, there's a whole bunch of different types of stem cells we'll talk about in a moment. And generally, cells lose potency as they differentiate. So I kind of like to think of this as an ant climbing a tree because it involves stems and their stem cells. But basically, if you have like an ant climbing a tree, you can think about it as the number of leaves that it can reach, right? Maybe there's 100 leaves initially, but then once it picks a branch to go down, maybe there's just 50 leaves now. And then it might pick a different stem to go down, and now there's like 3 leaves that it has the option of, right? And generally in our body, cells don't go backward. So we'll talk about this. So I said cells don't go backward. I've started this table of stem cells with iPSCs, which are induced pluripotent stem cells. These are stem cells that are made from reprogrammed adult tissue. So for example, I go in a clinic, they take a bit of my skin. My skin is not, in fact, a stem cell. It cannot create a whole bunch. There might be a couple adult stem cells in there, but for the most part, it's just purely already differentiated. It's just fibroblast. It's just my skin. There's a couple different ways to do it, but you add different chemicals to it, and they basically tell the cells, hey, go back in time, and it'll turn back into a stem cell. Most people don't know about these, and they're kind of the industry standard now. They're very nice because you know the genetic information of the person you're taking them from, which is very helpful, especially if you're studying diseases. You don't have to guess if the material you're starting with is diseased. You don't have to try to like check the DNA of it and then get it to survive, right? And there's a lot of adult tissue you can come back to, right? You don't have to kill someone to make an iPSC line. You just take like an inch of their skin. They have really high potency. They can turn into most things. The trick is we don't necessarily know how to turn them into everything right now, but but they're sort of parallel to embryonic stem cells. They have a pretty long lifespan. And when I talk about lifespan, I'm not talking about how long the cell can survive until it dies. I'm talking about how many generations of that cell you can have before it kind of senesces and it stops reproducing, or before it differentiates and you stop having stem cells, right? They've turned into something else now. And that's actually kind of one of the hardest parts of culturing stem cells is not they're difficult to keep alive, but the hardest part is keeping them stem cells and not having them turn into something else because that's what they're made to do. They're not made to just stay in stem cell state all the time. And these are pretty high quality, but it's very variable. They can be high quality, but obviously it depends on who made them, how well they made them. These are human made, so if you do a bad job making it, it's going to be a bad cell line. Then we have embryonic stem cells. So these are from a blastocyst, which I talked about a little bit on the last page. 4 to 7 days after the egg and sperm meet, you have a blastocyst. And these are basically what iPSCs are mimicking, right? They have really high potency, they have really long lifespan, they're really high quality. And that's because these are the cells that the whole human body grows from, basically. Obviously, a lot of ethical issues with these. We'll talk about that later. But this was for a long time the standard just because they're incredibly good at what they do. We have fetal stem cells. So these can be from fetal tissue, which is icky and gross, but it can also be from amniotic fluid. And that's mostly what fetal stem cells are from now. I don't actually know any uses or past use of fetal tissue, but in theory, it could have been used and probably has been for something. I really don't know. But these have pretty low potency. They have really short lifespan and they kind of have medium quality. They're not like incredibly amazing. They're mostly used for some types of like blood therapies and stuff. Like you can get blood from the placenta and then use that as kind of a stem cell therapy. But we have adult stem cells. So all of us have stem cells in us. It's how we heal when we get a cut. And these are pretty low potency. So what that means is my stem cells that heal a cut are not going to help me with a brain injury. They're not going to, my heart stem cells aren't going to help me if I have an issue in my liver. Right. So these are already, they've pretty much decided they can be like a couple of different cell types and they make more of that cell type and that's all they do. They have pretty short lifespans and they're pretty low quality, but it's still useful for therapies, obviously, because I mean, that's what a bone marrow transplant is. You're moving adult stem cells from one adult to another. So still useful, but not necessarily as useful as like an iPSC or an embryonic stem cell. So next slide, please. All good. Oh, go back. Wait, oh no, never mind. I'm sorry. Okay, so we've got a big history, but basically in the late 1800s, people were like, hey, we're studying the human body. We think it's made out of cells. And, do cells live forever? Do they die? So they found out after a couple of experiments that cells, in fact, the cells that our body are made of do not live forever. Different parts of our body have different half-lives of cells. So like my brain cells live for a really long time and don't get replaced as often, but my skin cells get replaced pretty often, right? And so they introduced this concept of stem cells being the place that all of these cells for healing and kind of that we're dying, we're being replaced from. And then in 1957, we had the first successful bone marrow transplant into a human. Very cool. And then actually in 1965 was when they first found or successfully how do I want to put it? They finally like identified which cells were providing the benefits to that bone marrow transplant, right? It's not that in 1957 we didn't know it had healing properties and we didn't know, but like in 1965, finally found those cells, right? Adult stem cells are very hard to find. There's low numbers of them. And then in 1981, We have the first person to isolate and grow embryonic stem cells. These are actually mouse stem cells, not human stem cells. And that's kind of where embryonic stem cell research began. And then 1998, in the University of Madison, we have the first human embryonic stem cells are discovered and cultured. Well, not discovered. We knew they existed, but it's the first time they're isolated and cultured in lab in vitro. So in 2006, we have basically the creation of the first iPSCs. As I said before, those are induced pluripotent stem cells. They're stem cells where you take cells from an adult human or, well, an adult, it doesn't have to be human. And then you take them back in time, basically, and turn them back into stem cells. And in 2010, we have basically, it's an addition to the 2006 discovery. The 2006 discovery, you're adding a bunch of proteins to these cells to make them go back. And in 2010, we're adding mRNA to these cells to make them go back in time. So it's a bit of a twist on the original discovery, basically. So there's a bunch of ethics. I'm going to kind of talk about some of the really big bullet points. There's definitely more ethical issues out there, but I just want to, there's some things that obviously you're going to be aware of, like embryonic stem cells. Yeah, ethical issue. But there's going to be some other stuff that I think maybe most people probably haven't thought about. So the first point is the source of your stem cells. So obviously embryonic stem cells, kind of an ethical issue because, as I'll get into it, you're kind of preventing a human from living. But if you're using iPSCs, generally less of an ethical concern because the person you're getting them from has presumably given consent for you to use those, and it's not really hurting them in any way. So embryonic stem cells, as I said, when you make a line, it prevents that stem cell, that cell from ever growing up. A lot of the time, these lines were created from test tube babies, the leftovers basically of those. Doesn't necessarily make it better, but it's just kind of, a lot of people see it as, well, they were gonna die anyway. Yeah, it's definitely an ethical issue there. And obviously informed consent, right? If you're taking cells from someone and they don't know it and you're turning that into a stem cell line, that's a huge ethical issue. You need to make sure that whoever you're taking cells from is aware not only what you're doing with it, but also all of the potential uses you have for it, right? Because as we'll get into the next page, there's some scary stuff that stem cells can do. And there's also some really great stuff for humanity. I, as a stem cell scientist, of course, think that overall the positives outweigh the negatives. But yeah, let's go on to the next slide and we can talk about that a little bit more. So we have therapeutic cloning. So stem cells can obviously be used to create tissues and organs, but that means they could also, in theory, be used someday to make an entire living creature, right? So if you have a stem cell line made out of your cells, there is a possibility that someday someone could make a clone of you. And basically, right now, everyone has said, don't worry, we won't do it. Which goes really well. So there's also an issue of access and equality, right? A lot of these stem cells are going to be used for therapies in the future to treat diseases. And the main issue with stem cells is they're extremely expensive right now. And hopefully they'll get cheaper over time, as most new technologies and emergent technologies do. But as things stand right now, it would be impossible for our society to be able to allow everyone to get these therapies. Insurance would be too crazy expensive. So it's a question of, and some of these therapies could make people live considerably longer, right? It could considerably improve people's just life in general and their quality of life, right? If you can prevent someone from ever getting Parkinson's, if you can prevent someone from, ever having a heart attack, these are huge things. And do we want it to be something where only the elite can afford it? Because currently that's kind of where we're at. So is it worth creating a therapy if it's only for the elite and not everyone's going to be able to access that? And of course, there's a huge potential for misuse. As I said, you could clone people. There have already there's already been one huge misuse step in the world of stem cells where, well, it's not really the world of stem cells, it's more like the world of CRISPR, which is a whole separate talk that I'm not giving. But there's huge potential for misuse. And right now, you know, there's laws and regulations around it, and everyone has said, hey, we're not going to do bad things with these. But how much do you trust people is the real question there. So, yeah. So we have a bunch of different regulations in the US. I don't actually deal with these directly. I deal with these indirectly. Basically, everyone above me deals with these, and then they say, hey, we've already finished all the legal stuff. Here's your cells. You can do your thing with them. So I don't actually know a whole lot about the specifics of these, but basically in 1996, the US government was like, hey, we're not going to pay for embryonic stem cell stuff. So if you're doing anything with embryonic stem cells, you can't get a grant through the US. Your tax dollars will not go toward that. Of course, states can fund that stuff. I don't think Wisconsin really does that. California is the huge funder of stem cell research in the US. But most stem cell research now is iPSCs anyway, so the US government does do some funding of it. Also, the NIH has a whole bunch of guidelines around stem cell research, and basically everything you do with them is kind of dictated by the NIH if you're getting any kind of NIH grant. So basically anyone in academia is following these guidelines. There's also a whole bunch about material transfer, right? So if I work for a company and another company's like, hey, we have a stem cell line and we want you to do this thing with it. There's a whole bunch that goes into that agreement to make sure that my company doesn't just like steal their line and start doing our own stuff with it, basically. There's also, I didn't put it on here, but the FDA does a whole bunch with stem cell therapies and kind of making sure that those are quality before they go into testing and stuff. The only approved therapy so far is bone marrow transplants, and it's only approved because we did it before anyone knew what stem cells were. So it's kind of a long story, but the FDA hates stem cells. So it's going to be a long time till you see a stem cell thing actually on the market. But yeah, we can go on to the next. So I was trying to think of the best ways to do this. So I'm going to go over kind of some of the big picture great things that stem cells can be used for. And then I'll go over in depth kind of what I did at my previous job. And then I'll have some time, a lot of time actually, for questions. I was expecting myself to talk a bit slower, I guess. So stem cells can be used to create like organs for transplant. There hasn't really been a whole lot of success in creating like a whole heart yet, right? People are getting kind of close actually, which is surprising and really cool. There have been eye transplants that have been done with like partially developed eyes, but if you don't have any eyes, it's still better than no eyes. So, and all of this, by the way, is like still in testing, right? So these people who are getting these treatments, it's as part of studies. It's not like something you can go to your doctor and be like, oh my gosh, I'm blind. Can I get a new eye? They're going to be like, no, you can't. So this is kind of a cool thing of the past, but I wanted to talk about it, somatic nuclear transfer. So basically, you take an adult cell, you take an embryo, you remove the DNA from the embryo, you take the DNA from the adult cell, put it in the embryo, and now you have an embryo that has the information of whoever you want to make something for, which is really cool. But now we have iPSCs, so we can skip the embryo part, which is great. And it's also just a lot easier. So I just put this in because it was really cool thing you could do. But iPSCs are obviously like better for many reasons. And then, so this kind of gets into what I do in my current job, but stem cells can be used for testing new drugs. So let's say I have a drug that helps someone who has Parkinson's, or at least I think it does, right? And I've tested it in animals that have Parkinson's and it's worked. Cool. Usually I would go on to testing in humans now. But Because we have stem cells, I could take some skin cells from someone who has Parkinson's, I could grow stem cells out of it, and then I could turn that into neurons or whatever cell type I want. And then I can test my drug on it. And that will let me know, what's it actually doing? I can see what it's doing in the Petri dish, but also I can make sure it's not going to have some huge, massive negative effect before I put it in a person, which is really cool. There's also, similar to that, if you want to look and study a disease, especially I differentiate stem cells into brain cells, which is super useful because if you want to look at a specific brain-related disease, right, especially some kind of genetic disease, you can take a skin cell from a person, you make your stem cells, and then you can watch them progress and grow. So you get to see how those cells grow and change over time. And you can do all sorts of different tests on those cells. And basically, you just don't have to wait for someone who has that disease to die to then cut open their brain and take a look at what's going on, right? It's not quite as great as looking at someone's brain because you don't get to see how all of the cells interact. And actually, there's a lot of work going into making special scaffolds that will hold all sorts of different types of brain cells that basically you create and then kind of throw them all together. But we don't actually know a whole lot about the human brain to begin with, so it becomes hard to simulate something you don't really know how it works. But it also works super well for all sorts of different diseases, all sorts of different body issues, and yeah. Also, just general studying of human development can be useful for that too. Yes. So some stem cell therapies. So I kind of talked about this. There's a whole bunch of different stem cell therapies out there that people are trying to do. It basically is kind of being used as a cure-all for everything right now, which we know how that's worked in the past. But also, basically anything genetic, this is super helpful for. Or anything where your body stops making something for whatever reason, right? So potentially diabetes and stuff like that could be useful for that too. One thing it doesn't work for is cancer. Just making sure you all know that. But basically, stem cells can be used to replace your cells that aren't working properly. And there's a couple of different ways that people who are making therapies are thinking about doing this. So the first way, these are basically all iPSC therapies, by the way. So cells where you take it from an adult and then you turn it back into iPSCs, just because it's so nice for knowing what material you're starting with. So basically, you can take someone's cells and you make whatever it is you need to make. Let's say we're making a heart for heart transplant. You make your heart and you put it back in them, and it works great because you don't have to worry about whether or not their body's going to accept it, right? Something you have to worry about with donations all the time is the body going to accept, right? Because your body knows that it's not its own material. And you can try to trick it by getting something that's kind of similar, right? You can think of it as like blood type. Like if you get someone with a close enough blood type, you can trade blood. If you get someone with similar enough like markers on your cells, you can trade organs. But it doesn't always work because unlike blood type, our organs have much more specific markers. So it becomes way harder to find someone who can actually trade with you, basically. And also, no one's going to give up their heart for you. Not typically something that people do. So if we could grow our own hearts from ourselves, that would be really cool. We could also, in theory, pick a group of people, right? I kind of mentioned that trading organs is sort of like trading blood, right? There's different markers on it. So if we find someone who has a marker that fits a solid amount of our population, you can just use that person's and maybe 20% of people can get a heart from that line, right? And so you would just need to have many people. The ethical issue with this one is that it really, it basically means minorities can't get treatment. Because if there's a cell line that's only going to work for 0.00001% of the population, no one's going to bother making it. So this option, Japan's actually looking at this option because they only really need 3 or 4 donors to take care of their whole population. But somewhere like America, where we have a whole bunch of people with a whole bunch of different genetic backgrounds, that becomes a lot harder as an option. There's also an option where you take one person's skin cells and you remove all the markers from it. So no one's body can say, you don't belong here, because there's no way to tell. This in theory sounds really great because it's a cheap option and everyone can use it. But the problem is, if that cell becomes cancerous, your body also has no way of fighting it. So it's sort of a double-edged sword. And this is part of why the FDA is hesitant to allow any stem cell therapy, because if you get a stem cell therapy, it's less likely that your body will be able to fight that if it becomes cancerous, even if it's your own cells. But this would be pretty much, you'd have to either do surgery or radiation, basically, to get rid of it. Those would be your only options. So, yeah. And then I have a fun video that may or may not work. It's just of some heart cells in a dish beating, which is really cool. I've seen this in real life, and it's just really fun to watch. But yeah, this is how most stem cells are grown. You're just in a flat dish. You've got them stuck to the surface, and then they turn into whatever you're trying to grow them into. So, yes, I'm open for questions. Oh. Oh, I'm so excited for Nancy's really hard question.
No, this isn't hard.
Okay.
It's really hard. No.
Okay. Okay. I've got to be really prepared.
Well, I don't know if it was the first page where you were showing the different, and we got down to the very first page. Yeah, right there.
Yeah.
Okay, on the right, that lower right. So that's a dendrite, right?
Yeah. So this is a neural cell.
Yeah. Okay, so that's
Dendrite.
my biggest interest, right?
Yeah. 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 Of course,
Yeah.
it's my biggest interest. I love them.
Yeah. Because you said what I'm always saying, we do not understand almost anything about the brain.
Oh yeah. So there was going to be a pop quiz in my lecture, and I didn't actually have my notes on me, so I was just kind of going off what was on the board. But in my pop quiz, I was, oh God, what am I even going on about? I completely lost my train of thought. But basically, yeah, that's what it was. That there's about 200 types of cells in the body. And I have to say about, because we haven't completely figured out what all the different types of cells in the human body are. And a lot of the unknown types are brain cells. I had the privilege of going to basically a neural-based conference, and some of what people were presenting were ideas of, we think that this is a new cell type because it has different markers from everything else and stuff like that. So it's really cool because it's like we don't even know all the cell types, let alone what they do, let alone how they interact with each other, let alone how it all grows and works together. Like, how do you make a memory?
Right. So, I mean, I look at that and I think of where we are with AI and this worshiping now at the altar of AI.
Yeah.
And sort of mesmerizing the public.
It's interesting.
That now this is going to be better than our own brains because we can go through data faster and we can assimilate it and we can synthesize it. And it's a hoax. I don't mean that AI is a hoax, but it's a hoax in the sense that we do not yet know how the human brain works. And that's where we need to be focused. This is just one of my lectures, so to speak.
I agree.
So I just want people to be aware of that and tuned into that, because we're being led down a path that's going to take us away from our humanity. But that's so I'm glad you're showing that, and I'm glad that's one of your main interests.
Yes, I have a quick
so important
note to add on. And I'm sorry I keep interrupting you because I'm so excited to say it. So basically my take on AI is, right, it's a tool, it's a useful tool, but it's not really any better than a supercomputer. It can't make anything new. Even the AI art that you see, it's never going to make something that someone else hasn't made something similar. Um, so, you know, it is a useful tool. And I don't think it should be ignored necessarily, but I do think that people are maybe getting a little too infatuated with AI, right? It's a cool new tool and it definitely has applications and uses, but it will never be able to make something original. It's not true AI. It's not truly, it's basically just a better way of searching the internet. Yeah. Oh yeah. Yeah, AI is not really intelligent. It's all you know, if you use it properly, it can be very useful, but very few people know how to use it properly at this point, I would say. Um, and it's basically just a different type of search engine.
I have a much more simple thing to that I just wanted to mention on your last slide when
Okay.
you showed the beating heart
Yeah.
cells in a petri dish.
Yes.
My mother was in heart research at the University of Wisconsin in the 1960s, and she did just that.
Yeah.
That's what they did. Is they were using pigs, but they used pig heart cells and watched them beat in a petri dish.
Yeah. Yeah. So it's really cool. I mentioned that I differentiate cells, and there have been times where one of my coworkers will call me over and be like, "Look at my dish, it's beating." And as you know, we're not trying to make heart cells, so it's kind of funny whenever it comes up. But yeah, it's very cool to see in person, especially because, you know, um, just the fact that over time they'd become like you might have a bunch of cells that are beating at different times, and over time they'll kind of sync up with each other and they'll actually start like beating more rhythmically. And it's very cool to see that that's just kind of hardwired into those cells to follow the leader and just work together. I did realize that I forgot to talk about something. So prior to my current job, I worked on a stem cell therapy actually that it didn't work out. We didn't have enough funding, but I did want to talk about it. And since y'all don't have as many questions as I thought you would, I'm going to talk about it. So I used to work for a company called Vascogen, and basically we were working on a therapy for people with ischemia. So ischemia is a symptom of diabetes, but there's a couple other diseases that it can be a symptom of. And basically, the blood cells in your extremities die off, which means that all of those cells in your extremities can't get any oxygen, so they die too. And basically, currently the only treatments are you can surgically move some of your larger blood vessels from different parts of your body to those extremities, and kind of hope that they connect to the rest of your vascular network, or you can amputate. And you can just amputate till you can't amputate anymore. So it's really not a great way to live. And basically, our stem cell therapy was we would take stem cells and we would make vascular progenitors out of them. So vascular progenitors are basically, they're kind of like an adult stem cell in that they can only make a few different options, right? So they're specifically made we would specify them to a point where they could make anything that was necessary for vasculature, but they couldn't, for example, make a brain cell if we put them in you, right? And then we would inject them into, we only got through animal trials, so we injected them into mice. And basically, the vasculature would either grow and connect to vasculature already in the mice, or it would just die off. And it was working pretty successfully. So there's a lot of hope out there for future therapies and such to be made for big issues.
Hey, Vivian. Oh, sorry. I'll go next from the back. So I have type 1 diabetes, and many of my family members do, and I know one of the potential applications was to recreate pancreatic cells or
Yeah, yeah.
beta cells out of stem cells, and I wonder how that's going.
I do not know specifically, but I can tell you that that absolutely makes sense as a way that people are trying to make that happen. Um,
I was just wondering what the status of using stem cells in osteoarthritis treatment.
Yeah. So I don't know specifically about like all the different treatments out there. But definitely, and I'm not really, it could definitely work for arthritis, but I haven't actually read specifically on that, so I have to apologize. I can't really answer your question.
Okay, because I know it's being done.
Yeah.
And pretty. I
Um,
don't know. I don't think insurance won't cover it.
Oh,
So.
no, no, no. Yeah. Sorry. Yeah. It's so right now, if you are really interested in a potential stem cell treatment, I would maybe, so here's the thing. You probably have to live in California because that's where all of the that's where that's where all of the money is. So actually, so I mentioned that California gives a lot of grants, right? So they only give grants if your company's based in California, which means you have to have a California headquarters there. And a lot of the ways that therapeutics will get around this is they'll make it so that the doctor that they're getting all their patients from and that they're sending the stem cells from to put into people is in California. So a lot of this research goes on directly in California, and a lot of the stem cells and other stuff is made elsewhere. But if you are really thinking about getting on that train, I would try to figure out what research groups are working on it and figure out what doctors are working on it and contact those doctors and say, hey, I have this issue and I know you're testing a new radical therapy and I'm interested. And, they'll probably say, oh, sorry, no. But they might say yes. I don't know. I can't tell you what they're going to say. But yeah, a lot of the times those doctors already have a list of people who they're seeing who they can try that for, unfortunately. So it's a hard thing to get a stem cell treatment. There are countries outside of the US that you can get a stem cell treatment, sort of like illegal surgeries that you can get outside of the US. I would not recommend any of you do that, just because obviously much lower quality of service. And also, something that's really serious that you need to think about if you're getting a stem cell therapy is what level of differentiation the stem cells are at. Generally speaking, you don't want to just like have straight up stem cells injected into you because they can turn into anything, like literally anything, right? So usually you want some kind of progenitor, and a lot of stuff that's like organs no one's successfully fully grown yet, so it's not really an option yet. Just, I don't know, food for thought. Also, it's going to be expensive. So, yeah.
Uh, when this became quite the research on stem cells became quite controversial soon after the developments, about 25 years ago, after Thomson made his big forward advancement at UW, and he became featured at Time Magazine as Man of the Year, if you remember, and there was big concern. I'm leading to a question which you've already partially answered, but anyway, there was big concern about the ethics of stem cells, especially the embryonic stem cells, and it became very prominent in the state legislature, if you remember, and the elements that were concerned in the state legislature were also the business elements, and they were competing with one another because the business elements wanted the business, and the ethics elements didn't want the research, and I think that's partly led to the Institute for Discovery on the UW campus, which was a entity that combined governmental research and business.
Mm-hmm.
And I think that's what's made possible some of the stem cell businesses here and research here in Wisconsin. My question is, a lot of these things have become obscured over the years, but other than California, are there centers for research in stem cells? And secondly, centers for stem cell businesses generating stem cells other than California?
Yes. So California is obviously a big one. Japan is a huge one. Their government put a good amount of money into stem cell stuff. So they're kind of one of the leading nations actually in stem cells, and then kind of the US. But Boston is also huge. They just have a big biotech hub there in general. So stem cells aren't necessarily like the main business in Boston. Biotechs are, but most stem cell companies are biotechs. So from that, there's a big hub in Boston. Madison is actually a pretty big hub itself. And oh, I'm forgetting it. There's a city down in the south too. But yeah, there's limited options actually for people who are working in stem cells. You're pretty much in California, Madison, Boston, or like one or two other cities. Just because all of the materials you need and sort of like, how should I put it? Like my company currently works with several other companies that are in the Madison area just because they make products we need. Right? And that's really convenient.
Big concern that if they hadn't developed the United States, that we were going to export the whole thing, but research it all to a foreign country. That was a big concern.
Yeah. Yeah. So one of the big concerns at the time was that if the US didn't do stem cell research, someone else would. Yeah, that's absolutely happened in Japan, right? Japan is very much into stem cell research. And also China's getting into it too. So, and obviously there's stem cell research around the world, right? There are places in Europe that you can go and do this kind of research as well. But the main hubs are America and Japan currently.
You mentioned Parkinson's. Do you know if they're using stem cells to treat Parkinson's?
Yeah, so there's definitely a lot of interest in Parkinson's currently, just from pharmaceutical companies in general, because there's a large number of the population that have Parkinson's. So it makes it a very potentially lucrative option for them if they can find a cure for Parkinson's or something that can even prevent Parkinson's. I don't know specific research, but I know for a fact that there's a lot of stem cell research going into Parkinson's.
Question for you.
Yeah.
Well, first of all, thank you, Vivian, for this presentation. The second question is one of your first slides had RMA in terms of
Oh, mRNA.
yes, thank you. And I was wondering if you could help me understand that, because I think that was one of the things that was involved with the COVID vaccines
Oh, yes. Okay.
and what the ethical.
We're in a whole nother presentation now, guys. So raise the hands. Who knows what DNA is? Let's start here. Okay, good. We've got a good group. So DNA is basically genetic information that's in all of your cells. It's identical to all of your cells. All of your cells have the exact same DNA. You can think of it as kind of like a cookbook. Everyone's got the same cookbook. They can all make the same things. The thing that make your cells different are which recipes they are told to make, basically. So what your body's ordering from them, pretty much. So, and that's also why we can make iPSCs possible, right? Because if we take a skin cell, it has all the information to become a brain cell. It's just not using that. So basically, we've got our DNA. And if you think about it, when our cell makes a new cell, it actually kind of splits in two. So it's kind of half new cell, half old cell for both cells. And the DNA in your body has to get split, and half of it needs to be new as well. Actually, at the very end of my presentation, I put a picture in for this in case if anyone asked about DNA. Yeah, keep going. Okay, here we go. DNA replication. So if when your body makes a new cell, it needs to duplicate its DNA for the new cell because it needs to have all the stuff that the other cell had. So basically what your body does is it takes your DNA, which is this double-stranded helix, it kind of straightens it out, And it basically like unzips it like a zipper. And then it puts new pieces of RNA in places, right? mRNA is a special kind of RNA. So we're using just normal RNA to build our DNA when we split cells in parts. But our DNA makes proteins for us. And that's kind of how everything in our body gets done, right? So it's going to be making the new proteins to make the new cell walls, to make the new Golgi bodies, to make all the new parts of your cell. And mRNA is basically your body will come through and it'll read a piece of DNA and it'll say, cool, I need these base pairs, right? It's basically reading one side of the DNA and then it's getting new stuff on the other side based on what it needs. And that new piece then detaches and it floats off, and that's mRNA, right? And that's basically like copying from your recipe book and taking one recipe, right? So now you've got this recipe floating around in your cytoplasm. That's basically just like a little copy of a piece of your DNA. And there's a special kind of protein that will attach to it, and it basically reads that recipe and it says, okay, these are the different chemical parts that I need to put together to make what this recipe is telling me to make, and then it will make a protein. So the original iPSC discovery was you add all these different proteins to your cell culture and they go back in time. But proteins are kind of hard for people to make. It's not like super difficult, but you have to basically the standard method is you take bacteria, you take their genome, you either you insert whatever it is that you want, whatever protein, and then you put a whole bunch of markers on it that say, just make this, just make this, just make this, just make this. And then the bacteria becomes not really as interested about staying alive and more interested in making whatever it is you asked it to make. And it produces a whole bunch of that protein, and then you have to purify that protein, and then you can use it. So if you just put mRNA in with the cells, if you can figure out what it is and you can figure out how to make it, which CRISPR has helped us with a lot, and that's kind of why this development could be made, was all because of CRISPR. And I really don't want to get into CRISPR, so don't ask me about it. But but basically, you could now make this mRNA, and you can just give that to the cells. So you can skip the whole bacteria step. Just give it straight to the cells, and the cells will go, cool, that's a protein I should make. And they'll make the proteins themselves that they need to go back, basically. So, yes, that's
I
amazing.
just wanted to.
Yes, yes,
M
it
stands
does.
for messenger.
Yes, it's messenger RNA. Yes.
So it's the RNA that's telling the cell what to.
Yeah, basically. Basically, yeah. Yeah. You can think of it as literally like the cell copying down a recipe from the DNA and then just kind of throwing it off, and that recipe card is the mRNA.
Okay, I have a two-part question. So
Yeah.
my cousin has aggressive leukemia. So they did a CAR T cell treatment.
Okay.
So they took out his white blood cells, sent him away to be re-engineered, and put them back in.
Yep.
But I'm assuming that's not stem cells, right? It's duplicating his own white blood cells. Would
Yeah.
stem cells be better? Is that right? It would.
It's so it depends on if they took adult stem cells from him and re-engineered those, or if they just did the white blood cells. I'm not positive exactly what all of that stands for, so I can't tell you for sure, but I think they probably did actually take some adult stem cells from him and re-engineer them. And then just because that would be so much more effective, because they'd be reproducing the white blood cells. Otherwise, you would need constant retransfusions of the new white blood cells.
Okay. And then they're supposed to fight the cancer and those new
Yeah,
re-engineered white blood cells.
with any luck.
Yeah.
That was me trying to cross both my fingers. It didn't work. But yeah.
Other questions? Okay.
Given you said you've been going to conferences, given the current status of research, are there any potential developments that we should be watching out for?
Ooh,
Soon
okay.
or within reasonable time?
Yeah. So the conference that I actually went to was not for stem cells, it was specifically for brain cells. So I have a whole bunch of cool information about the brain that you can look out for. Stem cells themselves, I would say, definitely, um, I think a lot of it's going to be kind of smaller news for a while, right? I think definitely like stuff getting approved in other countries will be big news, but it's going to be a very long time till anything's approved in the US because the FDA is very afraid of cancer. I personally, as a researcher, think it's a bit silly because if you're going to die of something else, you might as well get that treated and maybe have a high risk of cancer in the future. But you know, the FDA is very worried about potentially someone getting cancer from one of these treatments, and it is a big possibility, right? Um, so I would say, right, a lot of the stuff that you're going to be seeing is people are trying this new therapy. People are thinking about doing this, right? Something that's really cool is people are getting really close to growing a heart. Usually in pigs, actually, which is kind of funny. You can grow a human heart in a pig now, maybe, hopefully. So I would say, you know, organ transplant is going to be probably a larger thing that you see in the US as opposed to a therapy of, you know, we're going to give you this injection and it will cure whatever. That's going to be more of a something that happens in Japan and other countries first, I think.
Other questions? Oh. Okay.
I think we've all heard this. There's one chiropractor that advertises on TV pretty much day and night about all those various treatments. It usually involves an ultrasound or
Oh, yeah.
some kind of hocus pocus that way, rather than pop and snap and all that. Anyway, with one of his ads that he goes on and on about in the course of this treatment with this ultrasound or whatever, it generates stem cells to help cure your ailment. Is that such a thing?
No,
Sounded pretty easy. Or
that's not a thing. I can 100% confirm that's not something that is going to invigorate your stem cells or make any new ones. So, I know one thing definitively today.
We have time for one more question. Anything else? Oh, Nan, last question.
Very basic, Vivian.
Okay.
What happens to the cells when you're done working with them? I mean, you think about all the places that research is going on. What happens to those cells?
Yeah. So how do I put this? Okay. So it depends on what you mean by when we're done working with them. Because, so for example, if I'm just growing my stem cell population, I might start off with like this many stem cells, right? And I'm going to feed those for a few days. And then I'm going to take 50% of them and I'm going to put them in a bigger flask and I'm going to take the rest of them and I'm going to bleach them and kill them and throw them away. And I'm going to keep doing that for a couple of weeks. And so all of that waste is being basically just killed. Because you can't just have like human stem cells floating around in the water supply or something crazy like that. And then basically when we make our final product, right, whatever it is, so we mostly make progenitor cells actually. We make, and then we freeze them down. We cryopreserve them. So we're going to put them in a special solution that basically makes the outside of the cells porous, which prevents them from popping when they freeze because Water expands when you freeze it. Fun fact. We make them a little bit porous. We freeze them down, and then we keep them in. Basically, you put them at like minus 80 degrees Celsius for a while before you put them in liquid nitrogen. And then we ship them to whoever is asking us for them. And they take that little vial of cells and they thaw it and they finish differentiating them. And the reason that we don't fully differentiate them in-house is because brain cells don't freeze very well, but neural progenitors freeze all right. I don't know if that answered your question.
Sort of. Yeah.
Sort of. Is there a way I can elaborate? Can I make it a better answer?
It was a very primary question, so it's okay.
Okay. Okay. Yeah. At my previous job with the vascular cells, we did something similar where, you would grow them up. We actually had a little bit less waste in those because the whole like passaging them forward thing is to keep them in a specific growth cycle. And depending on what growth cycle the cell's in will depend on what it might want to differentiate into, which is a whole separate thing. But basically, there's a little less waste from that, but then we would make our vascular progenitors, and we would also freeze those down before we sent them off to wherever. And in that case, they didn't get differentiated anymore. They just got straight injected into whatever was getting tested with them. So
Thank you so much, Vivian. That was so interesting. Thank you. We appreciate it.
thank you. All right, let's turn this guy on.
Next week, we have Danny Weaver and the Mennonite Peace Initiative. So come back for that. Thank you.